We're at the American Astronomical Society meeting in Seattle, Washington, and I'm delighted this afternoon to be talking with Dr. Carolyn Porco, who is the lead investigator for the imaging experiment on the Cassini mission to Saturn. Since 2004, Cassini has been at Saturn, taking amazing images, spectra, all sorts of scientific data, and we're going to be asking her today about that mission. Carolyn, welcome. Thank you very much for doing the interview.
Well, thank you for interviewing me.
So let me start by asking, first of all, how this happened. You didn't just wake up one morning and decide to send a probe to Saturn. This has got to take a lot of time and effort and a lot of preparation. You and your team must have put in a lot of real hard work to make this happen. Tell us, please, how such a mission comes about.
Well, first understand that as enunciated by NASA and the people who formed NASA way back in 1958, the plan for exploring the solar system was really involved three steps. Right from the outset, they had this figured out. This is what they were going to do. We were going to send reconnaissance missions to all the planets. So these were quick flybys. We're even using the language of the military from which NASA derived, right? Reconnaissance. We're just going to sweep by and in a very short time just gather as much information as possible. Second step involved putting orbiters around each planet, in turn. And having an orbiter mission allows you in-depth investigation. You can monitor changes in the system. You could see how one system interacts with another over time. And so it's just a tremendous step forward to actually be there, physically present, so to speak, by proxy and observing, just quietly observing in the background. And then for those bodies that have solid surfaces, the third step was to bring a sample back to Earth, okay? And so obviously we've done all through the third step for the moon. I guess you can consider what we've done on, comets with stardust as completing that third step. But when it comes to the Saturn system, after Voyager, we were ready for step 2. It's time to put an orbiter around Saturn. And of course, it didn't necessarily have to happen that putting an orbiter around Saturn was going to come right after putting an orbiter around Jupiter. The way things politically go, we might have gone off in a different direction and decided, well, we're going to do asteroids or something else.
Neptune, Venus could have happened also.
Right. Other things could have happened. But Saturn was so compelling because it is such a phenomenologically rich planetary system. You can address an enormous breadth of scientific issues that are important for us, understanding our cosmic neighborhood, understanding the origin of the Earth, understanding the origin of life on the Earth, understanding the climate of the Earth.
And so you think it was an easy sell then? You could make a really compelling case to NASA that this was a really important place to go.
Right. I was just very junior at the time all of this was happening, but there were senior scientists who were making the case that we really needed to send an orbiter mission back to Saturn, and we needed to supply it with a probe that could investigate Titan. Because Titan was, in everybody's mind's eye at that point in time, Titan was the body that held great promise for there being kind of an organic laboratory on the surface from which we might learn tremendous things about the chemistry leading up to the origin of life. Nobody expected we were going to find living organisms on Titan, but that doesn't matter. There was still an enormous amount to learn about what organics do when they're present on the surface of a body. Because remember, the organics on the surface of the Earth have been destroyed, just free organics have been destroyed because of the oxygen in our atmosphere.
And the geological processes, surely, rocks being turned over, yes.
Right, all that stuff. So Titan was, in everybody's mind, the place to go. And Titan was, in some sense, a disappointment with the Voyager missions because the absorbing and scattering processes of the Titan atmosphere were exactly mismatched to the capabilities of the Voyager camera. Where the Voyager cameras were cutting out in sensitivity as you go to longer wavelength, that's where it turns out you could stand a chance of seeing down to the surface of Titan in the near infrared if you knew what spectral regions to look at, what spectral windows to look in. So between the end of Voyager and getting Cassini rolling, people copped on to this, that there were spectral windows you could actually see down to the surface of Titan, and we equipped our cameras with those filters.
So you could penetrate the fog and have a hope of seeing what the surface features were going to be like, and whether there were lakes, rivers, or whatever.
Whatever, and yeah, and we utilized that trick in equipping our cameras. And of course, there are infrared instruments that have no trouble seeing down to the surface of Titan on Cassini I'm talking about. And then there's a radar instrument. The radar instrument is basically a copy, more or less, of the radar instrument on the Magellan spacecraft that mapped the surface of Venus. So we were going hard on Titan as well. And then, of course, the Europeans built the probe to send to Titan. So the short answer to your question is that there was so much to be learned about Saturn that that was the planet that we wanted to go to next. And people who senior to myself argued that we should get a mission started, and they joined with the Europeans, and so it became Cassini.
Now, it sounds like there was almost an embarrassment of riches of things that you could look at. And you can't send a spacecraft of 100 tons. You didn't have that kind of capability. Cassini was 4-ish tons, right? Something like that?
At launch, Cassini was nearly 6 metric tons at launch, but more than half of that was fuel that was expended in the Saturn orbit insertion maneuver.
So you couldn't put anything you wanted on board. There was only a finite number of instruments that you could put on board. Was there a selection process? Was there a competition? And was this gentlemanly or knife in the back kind of competition?
Well, there were certain instruments that were deemed so important, they were called facility instruments. They were going to be there. They were going to be designed with the help of the science teams, but they were going to be built by JPL, effectively.
Okay. Right.
I think one of them, in fact, was built by another organization, but that's a tweak in my story. And then other instruments were solicited, but there had been design studies, and it was fairly well known what instruments had to be on Cassini. I can't recall, to be honest with you, if there were any new instruments that were added just because some group proposed them. Maybe that was the case. But there were design teams that were called together to determine just exactly what we needed yet to learn about the Saturn system. I, in fact, was on the imaging design team. So what we did, and I'm sure all the other investigations did the same thing, was just before it got started, just figure out what questions did we really need to answer about the Saturn system that could be addressed with the camera system, and then, what were the most important questions, and therefore, in light of those questions, what were the capabilities that the camera system had to have.
Okay.
And so that was the role of these design teams that met. And then they reported back to NASA and said, if you really want to do something at Saturn that's going to, knock people's socks off, make sure your camera does A, B, C, and D. And I'm pretty sure it was the same for other instruments. And so that's what happened after the group of us was selected to be the science team for Cassini. And that was November 13th, 1990. It's a day I will never forget. It was a phone call that literally changed my life and determined what I was going to be doing for the subsequent 20 years. 20 years later. But when we were all selected, we had those plans, the guidelines from the instrument definition teams, the science definition teams as well, and we basically set out to create the kind of camera that was proposed or suggested. And we added a tweak here and there. You know how these things go. You start out, you find out, well, we really would like it to have this capability, but the engineers can't figure out how to do it, so all right, we'll give up on that, maybe we can do this. And that's why there really needs to be a close collaboration between the engineers and the scientists to pull this off. And I'm really happy to say that we had a remarkable group of engineers at the Jet Propulsion Laboratory building the cameras for us. I'm not even an instrument person. I don't really get my jollies, building or thinking about instruments. But I have to say we had just a really lovely collaborative effort in building the cameras, and it shows. They work phenomenally well.
Well, the spacecraft got launched in 1997, and here it is 14 years later, and they're still cranking, they're still producing data. And of course the cameras had to have been tested and built years before. That's quite a shelf life, or quite a really robust set of instrumentation that you've got on board that spacecraft.
Oh, the suite of instruments being carried that are on the Cassini spacecraft is the most sophisticated suite of instruments ever taken to, certainly to the outer solar system. It's remarkable. I mean, you know, we started with Voyager. I think there was one computer for operating all, whatever it was, 8 instruments. But we have 12 scientific investigations on the orbiter alone. And each of them has sub-investigations, like the imaging investigation has 2 cameras. Each of them has their own microprocessor, and it's so many more capabilities built into the Cassini spacecraft that makes our job, make our job a lot easier. I mean, just as an example, with Voyager, if you wanted to command the camera, right, you wanted to say, turn here, someone down on the ground, I'm sure this was done with computers and software, but you know, it had to be calculated just exactly what kind of turn the spacecraft had to make at such and such a time. And then that information was uplinked to the spacecraft. Well, with Cassini, Cassini has on board in its memory banks, with all this compute power, has the trajectory of the Cassini spacecraft. It has the ephemerides, or the trajectories of all the bodies in the Saturn system. It has the position of Saturn with respect to the sun with respect, you know, it knows where everything is. Right. And all we have to do is say, now, turn to Enceladus.
And it does it on board by itself.
And then we send that command, you know, at this time, turn to the center of Enceladus. Or at this time, turn to this latitude and longitude on the center of Enceladus, because it also has, you know, it knows the shapes of all these bodies. And it can do that. And then it can do more. We can say, at this time, turn to the latitude and longitude of Enceladus and track that point for 30 minutes. It's remarkable what it can do.
So the spacecraft is moving, Enceladus is moving.
Everything's
it's tracking
moving.
this moving set of targets. Fantastic.
It figures it all out on board, and it's it's been great. It's just been, look at our pictures, it's been great.
The images in your lecture were stunning.
I know
They're
they
really,
are stunning.
really magnificent.
They're like my children, okay, right? It's just like raising children.
And you take great pride in them, and you really should. Now, you didn't know where everything was at the beginning. You've made discoveries along the way. Yeah. And surely some of these little tiny moons that you were showing must have come as, if not a surprise, then a wow every time you found a new one. How does that actually happen? Is there somebody really looking at every single picture? Is a computer trying to figure out where these new moons are?
Well, with the moons, especially the ones that you don't see you know, you can't resolve, and you know, they just look like any other blip, and you just have to look at all the blips and then figure out, can you fit orbits to them? Yeah, people do that sort of thing. But once we start getting an orbit, just even a rough orbit, then we go back and look again. Remember, that is the beauty of being in orbit. You can go back and check out something you discovered earlier. And so we knew this from the Voyager days. You know, it's interesting. I'm going to write a book someday about the planetary program, and actually the people involved in it, and the expertise that is represented by all these people who've been for a long time now. Some of the older guys on my team, they go all the way back to the Mariner missions to Mars. There's just a lot of expertise, and what's the word? I can't think of the word. Corporate know-how, if you will. You know,
memory,
corporate memory. That's it. Corporate memory. And so, anyway, this is just one example. On Voyager, we learned how to do a type of observation called a retargetable, which basically is, we've observed something. We know that at this time, this next opportunity, we want to go observe it again. But generally, by the time you're involved in a mission and you're there taking data, you've got every 30 seconds of the timeline planned. So you can't really do that unless you've thought ahead and you've said, I'm going to slot in placeholders. I'm going to slot in a placeholder here and a placeholder there. Call it a retargetable period of time where we have not pre-specified, at least early on, what we're going to be doing, but we allow ourselves, let's say, several weeks out to determine, okay, we're going to take this retargetable and we're going to look over there.
Because it's just the coolest thing that you've seen, and you absolutely need confirmation and want to be sure of what we really did see.
Yeah, so we had a lot of, in the early part of the mission, like the first 4 years, the nominal mission, we did a lot of retargetables where we went back, looked at moons that we had seen, we'd calculated some rough orbit, we knew, okay, we don't know exactly where it is, but we'll, you know, splatter this area over here with pictures and we'll hopefully catch it.
Right.
You catch it, you put that another data point into your model, you refine the orbit, you figure out where it's going to be at the time of your next retargetable, and you just keep doing that. And so you keep taking pictures of these bodies, and before too long you end up with really, really accurate orbits. So we're all over the orbits of the moons in the Saturn system. We know where those little suckers are.
Now you've got something really magnificent. We've got this incredible ring system, a disk system, which is also a prototype for the way we think planets form around stars.
You got it. Yeah.
And so you've got this really important system, but it's close by and things change quickly. Tell me a little bit about how you know what the particles in the rings are made of. You did mention in your lecture that you actually never get to see a particle because they're too small and the cameras can't resolve the individual chunks of ice in the ring. So how do you know sort of how big they are and what they're made of?
That's an easy question with a complicated answer. First, there are several experiments that can deduce the particle size distribution, okay? And stellar and radio occultations can do this because they can diffract light. Remember, you have signals going through the rings being observed.
From background stars that you're actually looking at.
Right, from background stars being observed by the spacecraft, or when the spacecraft goes behind the rings and the telemetry signals go through the rings to the Earth.
Oh, okay.
That's a much longer wavelength. That's radio wavelengths as opposed to starlight.
Okay.
And you can actually measure the diffracted signal from those events, especially with the radio occultation, because the beam is coherent. It's one wavelength. So you can figure out how the light is diffracted as it's going through the rings, and that can be modeled with the particle size distribution. So we know how the particles are distributed in size.
And that distribution is?
Well, the radio experiment can pick up everything from, let's say, I don't know, 100 millimeters, maybe a centimeter, all the way up to the biggest particles, like 5 meters. Stellar occultations can get all the way down to, the tiniest particles, pretty much, because it's starlight. It's a much smaller wavelength. But then there are other ways to do this. Just looking at the way that particles are, the ring system scatters light. Okay, you observe it from above, you observe it from here, you observe it, on the other side of the sun, you observe it on the same side of the sun. And these different viewing geometries allow you to sample the way the disk system scatters light in all 3 dimensions. And you can actually determine how the particles are distributed in height. And to some degree, you can at least add information about the particle size distribution, because if the particle size distribution is different, the way it scatters light in various angles will be different, okay? So the way we do this is we actually do this with numerical simulations. We mimic the particles in Saturn's rings on a computer, okay? And the inputs to that are, we can change the particle size distribution, we can change the particle number density, you can change the photometric properties or the way each particle scatters light at will. You can run one of these simulations, and then you can do, and I do this, actually, this is part of my research program. We actually, again, with another computer program, shoot light rays, simulated light rays, into this computer file of particles, and see, how those light rays get scattered in various...
And whether it matches the observations.
And whether it matches the observations. Okay. So, taking all these together, and applying it to figuring out what the particle size distribution is how we do that.
Very cool. Just to finish off, quickly can I ask you about propellers and gaps in the rings? You've got this astonishing set of pictures of these bizarre propeller-shaped things and these thousands and thousands of holes in the rings. Quite astonishing. Where do they come from?
Well, that's a good question. You know, it's related to where the rings come from. I suspect that what they are, you know, you can't get things really to form in the rings because it's within the rings, all the ring systems of all the giant planets in our solar system exist within their Roche zone, which means it is the region where the accretion, the natural gravitational attraction of bodies to want to make bigger and bigger bodies is frustrated by the tidal forces from the planet. So that's why the rings are still there, right? They haven't coagulated together. So it's difficult to form bodies there, but it's easiest, if you're going to do it at all, it would be easiest in the A ring because it's the farthest one out. And if you heard my talk, you noticed I said the larger bodies are on the outer edge of the ring. But nonetheless, it's I think probably more likely that these bodies were maybe the remnant shards of bigger, the progenitor bodies for the moon. I mean, excuse me, the progenitor bodies for the rings.
For the rings. Now, you did mention briefly an idea that's just floated up recently about how the rings actually came to be. What is their genesis? In the end, we really want to know where it came from. And of course, how long it's going to live. What's your best guess? If you were a betting woman, what would you say today is where did the rings come from and how long are they going to be there?
You heard me then talk about this most recent model, which I think is actually quite clever and beautifully done. And it says that as a natural outcome of the formation of the satellite system, which now the picture that is emerging as to how that might have happened is material is being accreted onto a growing planet from the solar nebula, but the intermediary step is a disk around the growing planet. So the stuff accretes onto the planet, but also accretes onto a disk. And if you imagine what happened as the gas accreting onto the planet it's getting near the end stage. The planet's gone, you know, almost there in its size. And the gas being accreted onto it is leveling out. Okay, so this is a place where I didn't mean leveling out, I mean it's decreasing. Sure. We're at the end stages. What this model says for the satellite formation is that you could get planets growing in such a system, okay, and these, not planets, moons, and the moons through drag with the gas around in this disk, even though there's very little of it because it's at the end stages, that gas drag forces these bodies to just spiral into the planet.
And so some of them go crashing into the planet.
Some of them go crashing into the planet. So the bodies that we see now may be just the last stages before the gas got completely swept away. But you can imagine that there were moons that might have, like the last moons that got swept into the planet. First, what happens to them is as they get closer, they'll be tidally ripped apart. And if the moon is differentiated, so it has a solid silicate core but an icy shell, then the first thing that's going to come off is the icy shell.
And so that's where the pure ice, lacking all the silicates in the rings, might have come from.
Might have come from. So it's a very satisfying model because it gets around that very thorny issue. Of course, it says that the rings, at least the heavy, massive part of the rings, probably was formed billions of years ago. And it's very likely, like let's say the A ring, might have been formed, or parts of the A ring, maybe the outer A ring might have formed later from a collision, from a breakup of a moon. It's hard to say. But the other notion that has been favored up till this point was just that there was a pre-existing moon already in the Saturn system. It got into the Roche zone, but got smashed completely. So it was collisionally disrupted. This one is more discriminating. The new model is more discriminating. It will just rip off the outer shell. So that's why it's appealing. It gets around the issue of why the rings are just so incredibly pure in having water ice, and yet the moons, the other moons of the icy moons of Saturn have, you know, they're mixed in, lots of dirty stuff is mixed in with them.
So could that silicate center still be there? Could that object still be there, or would it likely have fallen into Saturn
I
at
think
some
the
point?
idea is that it likely would have fallen in.
Okay.
Although, who knows, maybe the silicate core got bashed up, and maybe those are some of the, I doubt it, I doubt it. Anyway, we could speculate endlessly. I thought it was just a really interesting model.
Anyway, thank you again for a terrific interview, a fabulous talk, and congratulations on one of the most successful NASA missions of all time.
Thank you. On behalf of the whole Cassini project, I will accept your congratulations, because it's been the coolest.
Hell of a ride, and it's
Hell of
not
a
over
ride.
yet.
Oh no, it's not over yet. We have plans, detailed plans to go all the way out to 2017. That year was chosen because by that time, we will be at the height of northern summer. We arrived at the height of southern summer. 2017 will be at the height of northern summer, and that will be a full seasonal cycle if you take both hemispheres together. That will allow us to see and monitor and observe for a full seasonal cycle, like half a Saturn orbital period. And so that would be just tremendous, because we stand to learn a lot about what happens on the surface of Titan with its ponded hydrocarbons, what happens in the atmosphere of Saturn. We get to observe the changes in the rings for a longer period of time, so that allows us to refine rates of change, as you well know. So there's just a whole lot that we can learn. And this is like, right now, it's just a tremendous international resource that we have in orbit around Saturn, which, never forget, that planet is 10 times farther away from the sun than the Earth is. Yep. It is far, far out there. Yep. I'm fond of saying it's the farthest robotic outpost that humanity has ever established around the sun, and we should just squeeze every bit out of it as we can. So we're hoping we'll get the funding to go out to 2017.
Fantastic. Very last question. How can you top this? What are you going to do next?
Oh, I don't know. I may just, live on a boat in the Puget Sound or something after this. Living a nice, relaxed, peaceful life appeals.
Thanks again.
Oh, thank you.
It was great.